so today we're going to discuss inverse trig functions, like I mentioned. All right, so first we kind of need to just discuss a little bit about what an inverse trig function is. All right, so first we'll talk about kind of review what a regular trig function is, right? So a regular trig function we are given an angle, all right, and we answer a value. All right, so for example, we might say, okay, what is the sine of 7 pi over 6? Right? So this angle is what is given. And then we would answer, all right, negative 1/2. All right? So that's our answer. Oops. All right, of course, this is a value. All right, and 7 pi over 6 is an angle. All right, now if we don't remember why the sine of 7 pi over 6 equals negative 1/2, all right, again, it's very important, all right, that we remember our unit circle. All right, so 7 pi over 6 is the same as down here, 210 degrees is the same as 7 pi over 6. All right, our sine is our y coordinate at that angle. All right, so that's why it equals negative 1/2. All right, now an inverse trig function, well done, an inverse trig function goes the exact opposite way. All right, we are going to be given a value, and we will answer an angle. All right, so just kind of using the same things up here, although we really can't, so I'll explain this in a moment. But if I say, okay, what is the inverse sine of, we'll just say square root of 3 over 2? All right, so I'm given a value, all right, and I have to answer some angle. All right, and actually now I'm kind of annoyed at my unit circle since it only has degrees on there. All right, so let's do a better unit circle here. There we go. Okay, so let's maybe look at this one. There we go. Okay. So now, this keeps coming up, I do not know. All right, so looking at my unit circle here, all right, we said, okay, and we want to find the inverse sine of the square root of 3 over 2. So I say, okay, looking at my unit circle, remember sine are my y coordinates, all right? Where is my sine, the square root of 3 over 2? I'm sorry, yeah. Well, I see it up here, right? And I also see it over here, all right? So this is pi over 3, this is 2 pi over 3, all right? So theoretically, we could say pi over 3 or 2 pi over 3, all right? But are we really allowed to say this, okay? Can we say two different things at once, all right? Technically, when we're talking about inverse sine, the answer is no, all right? Now, sometimes you're asked within a certain domain, right, a certain range, like give me all values between 0 and 2 pi or between 0 and 360. Then you would say both of these, okay? But technically, when we talk about inverse sine, we're actually not allowed to include this 2 pi over 3, right? The reason why, all right, do we remember when we talked about inverse functions way earlier in the year, like Unit 2, all right? And we said that in order for a function to have an inverse function, all right, it has to be what we called one-to-one, okay? So a function must be one-to-one in order to have an inverse function. We are working on inverse functions, law of sines, law of cosines, well, in order to do law of sines and law of cosines. Good times.
I am just enthralled.
I bet.
I like the law part of it.
Right, yeah, there you go. All right, so we talked about this idea of a one-to-one function. And remember, the easiest way for us to tell if a function was one-to-one was graphically, right? And graphically, we said, okay, well, it has to pass both the vertical and horizontal line tests. Right, now we've all done the vertical line test many times, right? We see it first in Algebra 1, we see it again in Algebra 2, right? Basically, if we can draw a vertical line and move it anywhere across our graph of a function, if it never touches the function in more than one place, then we say that that is a function, right? If it's a relation, then we say it's a function, all right? Well, we can do that same thing with a horizontal line, and if it never touches the graph in more than one place, then we say it has an inverse function, okay? Well, we haven't really talked a whole lot yet about the graphs of trig functions, sine, cosine, tangent, that kind of stuff. We'll get into that, and we'll spend a whole unit on it, actually, our very next unit, all right? But we did talk about values of sine and cosine. So let's talk about y equals sine of x. And we call it theta often because we know that has to be an angle, all right? But when we talk about x's and y's, right, theta acts as our x, all right? So let's just pick some values, our thetas, our angles, on our unit circle, all right? So we have a lot of them. We know that we go from 0 to 2 pi, but let's just pick kind of some of our bigger kind of our quadrant right on our axes points, right? So when x is 0, if we look at our unit circle here, all right, so we go back to our unit circle. When my angle is 0, all right, remember sine is my y coordinate here, so it is also 0. All right, when my theta is pi over 2, which is 90 degrees, all right, my sine is 1. All right, when my theta is pi, all right, my sine again is 0. When my angle is 3 pi over 2, my sine is -1. All right, and then we come back around to 2 pi, which is all the way back around. So we're back at the same as 0 here, so we're at 0. All right, so if we just go ahead and graph this, this will be 1, this will be -1, and we can go 1, 2, 3, 4. All right, so this will be pi over 2, pi, 3 pi over 2, and 2 pi. All right, so if we go ahead and graph this thing, we know that we have the point 0, 0. So that will go right here on my origin. We have the point pi over 2, 1. So that would be up here. We have the point pi is 0. So it's back here. We have 3 pi over 2, -1. So that's down here. And then 2 pi is back at 0. All right, so if you connect this with a nice smooth curve, which will be a little hard for me on this little tablet thing that I'm working on. All right, it looks something like this. Now remember, we also talked about the idea of a periodic function, which are functions that just repeat themselves over and over, right? And that's actually what happens here. Son of a biscuit. Okay. Well, that didn't work at all how I wanted it to. Right, so let's try to get this in one fell swoop so it works how I want. Not very good, but it'll work better for this purpose. All right, so now, right, basically, we can just attach this over here, and it would go forever and ever. We could do it again and attach it over here. And this curve would go on forever and ever and ever. It just looks like a giant wave, okay? Now, does this thing pass the vertical line test? Sure, right? No matter where I draw a vertical line, I'm only going to touch it in one spot. Does this thing pass the horizontal line test? Anybody? No. Thank you. All right. Obviously, right? I mean, the x-axis here is a horizontal line, and we see that it will pass it, crosses it here and here and here and here, and it would infinitely. Okay. So technically, this thing doesn't have an inverse function, right? So how can we talk about inverse sine? All right. Well, the only way that we can talk about inverse sine, right, is to restrict my domain. All right, I have to say, okay, well, I'm only going to look from a certain x to a certain x. Okay, and for instance here, this would be -pi over 2. Right over here, it would be at -pi. Right over here would be at -3 pi over 2. Right, we keep going in the negative direction, keep going in the positive direction here. Okay, so where can I cut this graph, all right, so that it would pass the horizontal line test, all right? And we want to keep it around the origin, right? Of course, there's infinite places where we could, but I don't want to come way over here somewhere and say, okay, well, I only want to look from here to here, right? I want to keep it around the origin. So keeping the origin in mind, right, where can I touch every y value that this graph touches, all right, but only look at certain x values? All right, well, the easiest and best place around the origin is from here to here, right? Because then if I cut everything else out, right, if I take all of this blue stuff out and all of this blue stuff out, just imagine all that is gone. Now does this pass the horizontal line test? Someone shake their head or say yes. Yes. Okay. Now it will pass the horizontal line test. Okay. So basically, in order to have an inverse sine function, we have to say, okay, well, all right, typically the domain of sine, all right, is all real numbers, and the range is from -1 to 1. All right, well, we just said now we're not allowed to look at all of the real numbers, okay? Now I'm only going from -π/2 to π/2. All right, so this is sine of x. All right, well, so now if we want to talk about inverse sine of x, all right, when we do inverses, what happens with my domains and my ranges? What happens with my x's and my y's? Anybody remember? We talked a lot about inverses earlier in the year. In order to find an inverse, if I wanted to find the inverse of y equals 2x plus 3, how would I do it? Oh, you guys are going to fail this final exam so bad. Switch the x and the y. Yes, thank you, sir. You switch the x and the y. All right, so you would say x is equal to 2y plus 3, and then you would just go ahead and solve for y again. Okay, so that's how we find inverses. So with inverses, x's and y's just switch. Okay, well, when we talk about domain and range, domain is the x's, range is the y's. Okay, so these would switch. So now my domain will be -1 to 1, and my range will be -π/2 to π/2. All right, so this is very important to know. All right, if you plug anything into inverse sine that doesn't get between -1 and 1, you can't do it, right? Because it's not within our domain. All right, and you have to get an answer between -π/2 and π/2. All right, that is why, all right, we had to only choose π/3 here. All right, because if you go back to this unit circle, all right, well, if we remember, negative direction is clockwise, so -π/2 is actually down here at 3π/2, and then +π/2 is up here. So it's the right half of the unit circle, all right? But we have to be very careful, all right, because we can't say we can't call 3π/2 3π/2. We have to call it -π/2. 5π/3 is -π/3. 7π/4 is -π/4. All right, so let's see if this will actually let me draw here. Yes, sweet. Okay, so remember, if this is positive π/6, then going the same distance in the negative direction is -π/6. So 11π/6 is the same thing as -π/6. All right, so if this is positive π/4, then going the same direction in the negative direction, 7π/4 is the same thing as -π/4, positive π/3, -π/3, and positive π/2, -π/2. All right, so when you're talking about inverse sine, this actually is true for inverse tangent as well. All right, we only look at the right half of the unit circle. All right, so let's kind of make a little list of what we care about here. All right, so for inverse sine and inverse tangent, all right, our range, which is all we care about because that's what we're answering, okay, is -π/2 to π/2. All right, and for inverse cosine, and I'm sorry, this should be inclusive over here. All right, our range, which is what we must answer, is 0 to pi. All right, so these are very important. So with cosine, you don't have to worry about, oh, I'm looking at 3 pi over 2, I have to call it negative pi over 2. Or I'm looking at 7 pi over 4, I have to call it negative pi over 4. With cosine, you never have to worry about that. But with sine and tangent, you do. Okay, so let's go ahead and look at some examples here. All right, now it's also very important to note, all right, that inverse sine is also called arc sine. Right, and they all work that way, right? So inverse cosine can also be called arc cosine, and inverse tangent can also be called arc tangent. Of course, they all have to have. Say that again.
Go back to the last slide, slide number 4 for a second.
Sure.
Thank you, sir.
No problem. We haven't seen the graph of tangent before, but just for future reference, all right, tangent actually looks like this, like infinitely, which again, we'll talk about these graphs a lot more next unit, all right? So really, you can just cut all of these out, and then this little piece here will pass the horizontal line test? Sure. All right, so this again will be from negative pi over 2 to pi over 2, which is where this comes from. However, the range of this, instead of just being negative 1 to 1 like sine and cosine were, is all real numbers. All right, so with inverse tangent, you don't have that restriction on the domain. You can actually plug in any number you want. For sine and cosine, you can only plug in negative 1 to 1. All right, and I'll put up a handout as a material on Google Classroom that has all of that information on there also. All right, but let's go ahead and apply this stuff. All right, so we want to find the arc sine of square root of 2 over 2. All right, I guess it is also important to note here that this from negative pi over 2 to pi over 2 is the right half of the unit circle. All right, so whenever you're dealing with inverse sine or inverse tangent, you're only looking at the right half of the unit circle. And with inverse cosine, you're only looking at the top half of the unit circle. Okay, so if I want to find the arc sine of square root of 2 over 2, all I have to do is look at my unit circle, all right, and say, okay, arc sine is the right half of my unit circle. Sine is my y coordinate. So where is my y coordinate square root of 2 over 2? Can anybody tell me? On the right half of this unit circle, at what angle is my y coordinate square root of 2 over 2? Yeah, 45 degrees or pi over 4, right? So it depends on whether you're asked to do it in degrees or radians, right? If you're asked in degrees, 45 degrees would be the correct answer. If you're asked in radians, pi over 4 would be the correct answer, okay? So we can come back here and we say, okay, well, this equals pi over 4. And that's it. That's all we have to do. All right, so inverse cosine of 1. All All right, well, inverse cosine goes from 0 to pi, which is the top half of the unit circle. So all I have to do is look at my unit circle again and say, okay, only looking at the top half of the unit circle, where is my cosine 1? Remember, cosine on my unit circle are the x coordinates. So on the top half of the unit circle, where is my x coordinate 1? 0. Absolutely. So the answer to this is 0. All right, that's it. All right, arctan of 1. All right, arctan, just like sine, is the right half of the unit circle. All right, so we go over here, we look at our unit circle. All right, do remember that tangent is the y coordinate divided by the x coordinate. And on your unit circles that we filled out the first day in class, you should have all of the tangents filled out on there. All right, this was 0, square root of 3 over 3, 1, square root of 3, undefined. All right, so these would just be reflected, right? So negative square root of 3 over 3, negative 1, negative square root of 3, and then of course again this is undefined. All right, so our question asked us, where is, essentially, at what angle is my tangent 1? Right, that's really what all this is asking. So where, at what angle is my tangent 1 on the right half of the unit circle? Pi over 4, absolutely. So we just say, okay, this is pi over 4. All right, so inverse trig functions aren't that terribly difficult, right? It's just we're still looking at our unit circle, but instead of being given an angle and us saying a value, right, we're given a value and we have to say the angle. That's it. All right, so here, inverse tangent, again, right half of the unit circle. All right, where is my inverse tangent? All right, negative 1. Seven pi over 4, but remember we have to be careful. Is 7 pi over 4 between negative pi over 2 and pi over 2? Somebody's saying, no, Mr. Crouch, it most certainly is not. Remember, when we're going down here, we have to call these negative angles. So this is negative pi over 6. This is negative pi over 4, negative pi over 3, negative pi over 2. So what would I call 7 pi over 4? Negative pi over 4. Yes. So this would equal negative pi over 4. And that's it. No. Remember, we're not allowed to call it 7 pi over 4. Remember, back here, we said inverse sine and inverse tangent have to be between here. All right? Now, think of these as actual numbers, right? Some of you aren't very good at dealing with pi, right? I don't know why. You just think of it as 1, right? Like that's 1 over 2. That's 1/2. This is positive 1/2 in terms of pi, right? Positive, negative 1/2 pi, positive 1/2 pi. All right? So is 7 pi over 4, is 7 over 4 between negative 1/2 and positive 1/2? No, it's not. All right? You can kind of think of these as, if you want to think of them as decimal approximations, sure, right? Pi is 3.14, so pi divided by 2, this would be negative 1.57, all right, to positive 1.57, all right? All right, well, 7 pi over 4, all right, well, 7 times pi, even if we just call pi 3, that's 21 over 4. Is 21 divided by 4 between these two numbers? Absolutely not, right? It's 5.25 if you put this as a decimal, so it's definitely not between here. So we aren't allowed to call that 7 pi over 4. We have to use its coterminal angle. Remember, we've talked about coterminal angles. Just subtract 2 pi from it, right, and you get that negative coterminal angle that we need. Right, so if you call it 7 pi over 4 on the test, like you're going to be wrong, because we're not allowed to use 7 pi over 4. Right? We have to be very careful about that. Okay, so go ahead and try these just on your own. All right, remember arc cosine, we look at the top half of the unit circle. Arc sine and arc tangent, we look at the right half of the unit circle. Okay, so looking at this, arc cosine of negative square root of 3 over 2. So we go to our unit circle here. We say, okay, arc cosine, we're looking at the top half of the unit circle. On the unit circle, cosine are the x values. All right, so where is my x value? Negative square root of 3 over 2. That is over here. So 5 pi over 6. All right. This is the exact same thing, right? Except it's positive, right? So we're just saying, okay, right half of the unit circle. But where's my x coordinate? Positive square root of 3 over 2. Oh, well, that occurs right here. That happens at pi over 6. or 30 degrees if you're in degree mode. Right, and then finally, inverse tangent. That is now the right half of the unit circle. Right, and where is it? The square root of 3. So we go back over here. Remember, I wrote all of these tangents over here. Okay, where is my tangent positive square root of 3? That's up here at pi over 3, or 60 degrees. And that's it. That's all there is to basic inverse trig stuff from the unit circle. All right. Sometimes, in fact, oftentimes, especially when we start diving more into law of sines and law of cosines, all right, we'll be using our calculator a lot for this. All right. So calculator is, for the most part, pretty straightforward. All right. I can literally type it in exactly like I see it. The inverse are in blue right above their regulars, right? So for inverse tangent, I just hit second tangent, all right? And then we hit 4.84, all right? Now, we do have to be careful here, right? So if I hit enter here, 78.3, all right? Obviously here, I'm in degree mode. All right, if I go down to radian mode, and I do the same thing, I get 1.367, all right? Typically, when we use the calculator, we typically use degree mode, all right? Because for a lot of us, radians don't have a whole lot of meaning when they're not in terms of pi, right? Hopefully, from seeing the unit circle enough times, if you say, okay, if I told you the angle was pi over 6, you'd say, okay, well, I kind of know how big that angle is, right? But 1.367, if I was like, oh yeah, draw me an angle of 1.367 radians, you're going to be like, I don't know, right? But if I told you to draw me an angle of roughly 78 degrees, you'd say, okay, it's an acute angle. It's definitely less than 90. It's, not too far away from 90, so you could probably freehand an angle relatively close to 78 degrees, right? But this would take a heck of a lot more thought, right? So typically when we do calculator, usually we're in degree mode. So we can do all of these, right? So inverse cosine of negative 0.349. So 110.4 degrees. All right. Let's look at this next one. This next one's interesting. Inverse sine of negative 1.1. Bam. Why did we get an error? All right. Well, way back here, it said, okay, what is the domain of inverse sine? Negative 1 to 1. We're only allowed to plug in values between negative 1 and 1. All right. Is negative 1.1 between negative 1 and 1? No. No, it is not. Okay. So that's why we couldn't do that. All right. Now, arctan has that domain of all real numbers. So we're going to be able to do this one. Tan of 8.45. All right, so 83.3 degrees. Inverse sine of 0.2447. 14.2 degrees. What about this last one? Am I going to be able to do it? No ideas? 50-50 chance, right? Yes or no? It's a true or false question. Who has a guess? No. I like no. All right? Because cosine and sine work the same way, as in you can only plug in things between negative 1 and 1. 2 is not between negative 1 and 1. So we would get an error there. Okay. So now, if possible, find the exact value. All right, now typically inverse functions cancel each other out. All right, most of the time that is true. All right, and we'll use that fact a lot when we get to solving trigonometric equations. All right, but sometimes it's not. All right, and most of the time that arises from how we had to restrict the domain of the original functions in order to uh, allow them to have inverse functions. And I'll show you what I mean here in a minute. All right, but the rule of thumb here is that basically we always want to work from the inside out. Okay, so just like order of operations says, right? You do things inside first, right? So I'm just going to look at arctan of -5. All right. Well, what is the domain of inverse tangent? All right. So this is very important, right? We already said that inverse sine, all right, has a domain of -1 to 1 and a range of -π/2 to π/2, which in degrees is -90 degrees to +90 degrees. All right. Inverse cosine has that same domain of -1 to 1, right? We have to plug things in between -1 and 1. But its range was between 0 and pi, which in degrees is 0 to 180. I showed you that little piece of the graph of tangent, all right, and said, okay, well, because of how its graph works, its domain is actually all real numbers. All right. Its range, just like sine, is -π/2 to π/2. All right, so having this kind of available to us is convenient. All right, so I want to look at the inside out. All right, so I'm talking about arc tangent, which is over here. My domain is all real numbers. So am I allowed to plug in -5? Is -5 a real number? Sure is. All right, so these essentially will just cancel out, and I'll be left with -5. All right, arc sine, my inverse sine over here. My domain is -1 to 1. Is pi between -1 and 1? Ladies, is pi between -1 and 1? No. Yeah, I'm just looking at you two over there. No. All right. So we're not even allowed to plug pi in here. All right. So this is undefined. Right? You can't do it. All right. Go down here. All right. We're looking at inverse. We still want to work from the inside out. So we want to do inverse cosine. All right. Well, my domain is -1 to 1. Is 0.54 between -1 and 1? Sure is. So these will just cancel out and we say, okay, this is 0.54. All right, now we have to be careful here. What's different between this one and these previous three? Yeah, the inverse is on the outside. Okay. Now, so we still want to work from the inside out. All right. So what we want to do here first is just say, okay, what is the sine of 5 pi over 3? All right, well, if I go to 5 pi over 3, sine is my y coordinate. All right. So what is my y coordinate here? I'm circling it on the screen. Shouldn't be that difficult. -√3 over 2. All right. So this is the same thing as the inverse sine. That outside piece stays the same, but sine of 5 pi over 3 is -√3 over 2. All right, well, now this just becomes one of the simple problems that we just did. All right, so we say, okay, inverse sine is the right half of the unit circle. All right, and sine is my y coordinate. Well, I know I'm down here because that's just where I was. But when I'm doing inverse sine, am I allowed to call this 5 pi over 3? Is 5 pi over 3 between negative pi over 2 and pi over 2? No. What do I have to call it? Not just pi over 3. What is it when we go this direction instead of this direction? Negative pi over 3. Absolutely. So this equals negative pi over 3. Sure. Guys, you don't have to ask me to use the restroom. Like, we're big boys and girls at this point. We can just go. Yeah, I never make my students ask. All right. So here we're doing inverse cosine. So inverse cosine, my domain is negative 1 to 1. Is pi between negative 1 and 1? Nope. So can't do it. Yep. All right, so I know that it's going to be tempting to just always cross them out and put whatever is over here as your answer. That's not always true. Okay, so do be very mindful of that. Okay, find the exact value. All right, there's a very complicated formula that can allow us to do these things. And just FYI, that's how I know students are cheating on tests. When they give me this very complicated formula that I never teach my kids ever. All right. So if you try to do that on the test, I will laugh as I grade it and just mark it wrong. Right. So what we need to do here is we're going to use a little trick, right, that we've used a little bit before called U substitution. All right. So what I'm going to do, oh, and this should be inverse. This will always have to be inverse. All right. So what we're going to do, all right, is always let U, oh, son of a biscuit, equal whatever is on the inside. All right, so in this case, inverse cosine of negative 12/13. It's a U. All right, so now I want to get rid of this inverse. I don't like inverses. How can I undo this inverse? And we just did it over here a couple of times. What undoes an inverse? As long as it's within my domain.
The regular
Thank you. Yes.
trigonometric function.
Absolutely. The regular trigonometric function. All right, so cosine, regular cosine, will undo inverse cosine as long as this value is between negative 1 and 1. Is this between negative 1 and 1? Someone say, yes, Mr. Crouch. 12/13 is definitely not 1. All right, so yeah, so we can take the cosine of both sides. And when I take the cosine of this side, it cancels out the inverse cosine. And now all I have is this. All right, well, now I can draw myself a little picture. All right, now, inverse cosine only deals with the top half of the unit circle. Agreed? All right, so that means I'm in either quadrant 1 or quadrant 2. Is cosine negative, because this is a negative, in quadrant 1 or quadrant 2? 2. Remember, all students take calculus. In the first quadrant, everything, all trig functions are positive, right? So cosine is negative in the second quadrant. So I know I have to be in the second quadrant. And I'm going to call this my angle U, because remember, trig functions are always attached to this angle. Cosine, as far as SOHCAHTOA is concerned, is what over what? SOHCAHTOA. adjacent over hypotenuse. All right, so 12 and 13. Which one of these has to be negative? The 12, right? Because first of all, the hypotenuse is never negative. But second of all, from the origin, I'm coming to the left, which is negative, right? You can use your Pythagorean theorem, or if you remember 5, 12, 13 Pythagorean triple, this is going to be 5, and it will be positive because we're going up. All right. Well, now that I know all of this stuff is equal to u, really all I'm looking for here is the tangent of u. Well, here's my u and here's my triangle. Tangent is what over what? According to SOHCAHTOA. Opposite over adjacent. So opposite over adjacent. So this is simply 5 over negative 12. Done. That's it. It's not near as complicated as what it first looks when you look at this mess. Okay? Let's look at another one. All right, I think there's more to, right. So I'll do another one for you, and then I'll let you practice one. All right, this one I'll go over a little quicker. All right, so of course we always want to let u equal the inside stuff. And since this is between -1 and 1, I can cancel out inverse sine by taking regular sine. And of course, with an equation, whatever I do to one side, I have to do to the other. That's why I have to take the sine of this side as well. All right. Well, sine, we were dealing with inverse sine. So that's the right half of the unit circle, which means I'm either in quadrant 1 or quadrant 4. This value is negative, which means which quadrant do I have to be in? 4, because in the first quadrant, everything is positive. All right, so here's my angle U. According to SOHCAHTOA, sine is what over what? Opposite over hypotenuse. Now, which one has to be negative? Yeah, right, because it's coming down. And again, the hypotenuse is never negative. Right, you could use your Pythagorean theorem here. A squared plus b squared equals c squared. Right, or you could know that this is a 3, 4, 5 Pythagorean triple. Right, so since u equals all of this stuff, what I'm really looking for is cosine of u. Well, cosine is what over what? Adjacent over hypotenuse. So that's just 4/5. Done. So these really aren't that terrible. Okay. All right, go ahead and try this one. Okay, so let's take a look. Again, as always, we just let u equal this inside stuff. All right, and then to undo tangent, we can do regular tangent of both sides. Don't worry that this isn't between -1 and 1. Remember, inverse tangent is the only one where its domain is all real numbers. So this is a real number, so we're good there. So I can take the tangent of both sides. And of course, tangent and inverse tangent cancel out. All right, inverse tangent, which is what we were dealing with initially, like inverse sine, deals with the right half of the unit circle, so I'm either in the first or fourth quadrants. All right, this is negative. Of course, everything's positive in the first quadrant, so I have to be in the fourth quadrant. All right, tangent is opposite over adjacent. Now, one of these has to be negative. All right, it's going to be 4. All right, because 3, I'm going to the right, which is a positive direction, but here I'm going down, which is a negative direction. Again, you could use the Pythagorean theorem, a squared plus b squared equals c squared, or just know that this is a 3, 4, 5 Pythagorean triple. All right, so of course, now that all of this messy inside stuff is simply u, I'm just looking for the cosine of u. Cosine is adjacent over hypotenuse, so this is simply 3/5. Good times? Good times. Yep.
Why is it the fourth quadrant and not the second quadrant again?
Okay, remember tangent is the right half of the unit circle. Because it goes from -pi/2 or -90 degrees to +pi/2 or +90 degrees. So with inverse sine and inverse tangent, we only have the option of the right half of the unit circle, which is quadrants 1 and 4. With cosine, it's the top half of the unit circle, so it can be quadrants 1 or 2.
Thank you, sir. That makes it a lot more logical.
Excellent. Okay, so now we're going to look at this one. All right. Now, we haven't really been talking about inverse secant or anything at all yet. Okay. Well, that's fine. We don't really have to. We can still kind of use the same concept here in something that we've learned before. All right. So if u is equal to the inverse secant of 3/2, all right, we can still do our same trick here and just take secant of both sides, and we will get secant of u is equal to 3/2. Well, we're not a big fan of secant. It's not one of our 3 regular kind of main trig functions. Which of our 3 regular normal trig functions is this a reciprocal of? Anybody remember? Hint, it begins with a C.
Cosine.
There we go. All right. So, and we know that because of our reciprocal identities, that if secant of u is equal to 3/2, then we know that cosine of u is equal to 2/3. Yes, no, maybe so? Okay. So because secant is the reciprocal of cosine, it works the same way as cosine. All right. So inverse cosine deals with the top half of the unit circle, so quadrants 1 and 2. So inverse secant will do the same. All right. Now this is a positive value. Is cosine positive in quadrant 1 or quadrant 2? 1. All right. So I make my angle here in quadrant 1. All right. Cosine is adjacent over hypotenuse. All right. Now, this is not a nice Pythagorean triple, so we are going to have to use the Pythagorean theorem here. Okay, so I'll say a squared plus b squared is equal to c squared. Remember, c is always the hypotenuse. So this is 4, this is 9. So a squared is equal to 9. You subtract 4 from both sides, you get 5. All right, so a is equal to the square root of 5. Now this could be positive or negative, but since we're going up here, we know that it has to be positive. All right, well, now we do the same thing, right? We let all this messy stuff equal u, and this is a typo. That has to be regular sign. All right, so really all we're looking for here is sine of u. Well, sine is opposite over hypotenuse, so this is just the square root of 5 over 3. Good times? Great times had by somebody somewhere. Okay, so now this looks really messy, right? It's not. It's actually the exact same thing that we just did, but now we're going to have letters in there instead of numbers, okay? It's okay, works the exact same way. All right, so what I'm going to do is let my inside stuff equal u. And remember, arc cosine is the same as inverse cosine. How do I undo inverse cosine? Regular cosine. So I take cosine of both sides. I get cosine of u is equal to 3x. All right, now, because it tells us here that x is positive, right, between 0 and 1/3. So I know that this is going to be between 0 and 1, which is what we need it to be. Right? That's the only reason this is there. You don't really have to worry about it. All right. So we know that this is going to be positive. So we know that I'm going to have to be in the first quadrant. All right. Cosine is adjacent over hypotenuse. This isn't a fraction, though. Can I make it a fraction?
3 over 1.
Yeah. Just put that over 1. Right? So now cosine is adjacent over hypotenuse. So my hypotenuse is just going to be 1. Right? So now I still have to do my a squared plus b squared equals c squared. It's going to get messy. All right? So I guess I'll just call that a. So a squared plus b squared is equal to c squared. And you do have to be careful to square the whole 3x, don't just square the x, all right? So here we have a squared plus 3x times 3x is 9x squared. Whoops, that should be equal 1. All right, so now I can subtract 9x squared from both sides and then take the square root. Okay, and no, please don't be the students that do this. There's always multiple. You cannot just take the square root of 1 and the square root of 9x squared. Can't do it. All right. That only works with multiplication and division, not with addition and subtraction. Okay. So this is the square root of 1 minus 9x squared. All right, well, now that we let u equal all of this inside mess, really all I'm looking for is the sine of u. Well, sine is opposite over hypotenuse. Of course, anything over 1 you don't really need to do. All right, but that's it. All right, you guys can go ahead and try this one over here. But we've already done the work, right? Because it's the same inside. So this triangle's already done for you. Okay, so do keep that in mind. Those of you trying, I'm sure, have probably already gotten to the messy part. Just FYI, I don't make it be messy. I just kind of let you kind of leave it. All right, I'm not going to make you rationalize or do any crazy stuff like that. Okay, if you want to, sure, but you don't. I'm not going to make you do that here. All right, so here we do the same thing, right? We let u equal this stuff, all right, which we've already done. All right, so what we're really looking for is simply the cotangent of u. All right, well, cotangent is simply the reciprocal of tangent. So if tangent is opposite over adjacent, then cotangent is adjacent over opposite. Yes? All right, so this would just be adjacent over the opposite. And you can leave it like that. That's fine. If you want to rationalize it, you can, right? That's mathematically proper, right? But I'm not going to make you guys do that. We don't, I mean, do we really need to do a bunch more of those? Okay, they're there if you want to practice them, all right? But that's it for today, all right? So you can take the rest of the block and work on your Delta Math assignment, which is a lot simpler, all right, than what some of the stuff we did today, especially that stuff at the end. The stuff on Delta Math is just the basic stuff for today.